The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone. My name is Eric Larson. I'll be conducting the Inspire in Motion webinar series today and Thursday. We'll give everyone a few moments to come in. We'll get going in about 4 minutes. Until that time, if you look down in the chat window, you should see a link. It is the same link that is available in the little window or the background there, that slide. And that's where you're going to be able to get the material that I'm going to go through the course with. Really not going to do much in the way of having you do exercises because we are a little bit pressed for time. But everything, all the models that I use are going to be the ones that are in that download, so you'll be able to work along, and then you'll have all the material. That's actually all the material that we provide when we teach this class in its entirety, which is I don't know, about a 6-hour class in its entirety. But those are all the files that we use in that, so you'll have the availability to get all of the information that you would get in a standard class. So again, about 4 more minutes. We'll give a few more people a chance to pop in here, and we'll get going. Everyone is in a muted mode, so whether you are calling in by phone or have a microphone, you are all automatically muted by the webinar software. If you want to ask a question, you'll have the availability to do so in either the chat window, or if you raise your hand, I can unmute you and provide you the ability to ask the question verbally if you so desire. But that's it for right now. We'll give people just a few more minutes, and then we'll get going. Okay, well, it is now 3:35 here in the Eastern Time Zone. I'd like to welcome you all to day 1 of this week's portion of the webinar series. This is a multi-week educational webinar series Altair provides in the fall of every year. We like to pick kind of the hot topics that we cover, that are most applicable to those of you in education. This week we're going to be covering Inspire. They have, in the past, it has always been 2 days of Inspire, but this year we've decided to rebrand it or rename it Inspire in Motion, because I feel, and I think a lot of other people feel as well, that the motion capabilities of Inspire really now bring truly inspires awesome power into light. In the past, it's always been an analysis and optimization, and those are fantastic, very powerful. But now the ability to work in some sort of kinematic solution that allows you to simulate some dynamic system and analysis and analyze or optimize that really expands its capability. So this year we're going to do one day today that's going to be entirely devoted to structural and optimization within Inspire. And then on Thursday, we will meet here again, same time, where we will talk strictly about the motion capabilities within Inspire, and then how to go back and bring those back into an analysis and an optimization. Again, the material that you have is for today only. I will be providing a separate download link for the people who have registered for day 2 on Thursday. So if you're coming back again on Thursday, you'll have another download link that you can get the material from. Again, if you are just coming in, if you go to the chat window, you'll find a link where you can download the material. We'll go through what's in there in just a minute, but you can find that in there. And then let me just pop over here to this second slide right here. Just a few pieces of information before we get going. First of all, my name, again, is Eric Larson. I am the Technical Account Manager for Education here at Altair. It means I handle our relationships with universities, with university competitive teams, from more of a technical aspect of things. I do a lot of traveling around the country to do trainings, to do demonstrations, benchmarks, all that sort of fun stuff. And love to help you out, which leads, actually we'll skip this for just a second, which leads nicely down into here. If you are a member of a competitive team, Formula, Baja, Formula, Baja, Clean Snowmobile, the Design, Print, Fly, the ASME eFest, the Human Powered Vehicles, or the Student Design Competition, Rocketry, basically any form of competitive team, we would love to sponsor you. And sponsoring is going to get you access to all of our software. We'll provide you corporate level licenses to any and all of our software. Inspire is of course included in that list. And we'll provide you trainings as necessary, provide you support, really treat you like you were a customer and not a student organization. And information about that can be found at altairuniversity.com/sponsorship app. It's a very simple application to get sponsorship. Usually we can wrap things up in about a week, 2 weeks at the outside, and you'll have as many licenses of software as you want. If you are just kind of an independent student here, we do have a student version available, and it also is at altairuniversity.com, and then it's /free Altair Student Edition. That too just requires a quick form that you have to fill out, and we'll get you access to the student edition. The student edition does have some limitations in some of the softwares. They're very generous limitations, but it does have some limitations. For instance, if you like to use our high-end pre-processing and analysis softwares, there's I believe 100,000 node limit. So typically it's going to allow files that are going to be fine for academia, but it does if you are involved in a competitive team. You're much better off getting a sponsorship through us because there are going to be no limitations on that software. Yeah, and that's it. We'll touch on that at the end again as well. Just a couple of notes. Everyone is muted. As I mentioned earlier, the system automatically mutes you upon entry into the webinar. And that's just to keep, it's not that I don't want to hear from you. I absolutely want to hear from you, but it's just to make sure that we don't have that background noise. you'd be amazed at how many these webinars or meetings or trainings that we do, and we're hearing paper shuffling, people talking in the background, even dogs barking, and it just kind of takes away from the training experience. So it automatically mutes you, but as I said, I absolutely want to hear from you. So if you do want to ask a question, you have a couple of options for you. We have the question window where you can ask questions. Or if you raise your hand, I would be happy to unmute you. And you're free to ask a question verbally that way as well. So that's pretty much it. I would definitely want to get headlong into this into the software so that we can cover everything that we need to cover. What I'm going to do here, let me minimize this real quick. Minimize that, and we don't need that up. And I'm just going to come here. If you go into the folder or the files that the file that you downloaded is a zip file, and you're going to see in there 3 directories: student exercise solved, and PDF slide. In the PDF slide, and actually I got rid of all of these except for the total one. You're going to have this PDF file in here. These are all just each individual chapter broken out into its own PDF file. The file that you've got is going to be the entire class. So this is the PDF file that's typically used by many of the instructors when they teach the class. So they'll bring these slides up and they'll use them as kind of a background to their talking. And then additionally, at the end of each one of the chapters, if I can get down to the end here, it's almost there. There we go. At the end of each one of the chapters, you're going to see exercise 1. So this is the exercise at the end of chapter 1, generating your first concept design. And it's going to walk you through the things that we covered in that chapter and allow you the opportunity to work on those yourself. If we were doing this as a full day class, I'd go through a section and then I'd say, okay, now we're going to work on that exercise. But in this kind of abbreviated 2-hour, we really don't have the time to do the exercises. There's things that are far more valuable to be using our time for. But absolutely, these are great exercises for you to walk through on your own. Now, like I said, a lot of instructors will use these slides as a backdrop to what they're talking about. I'm a little bit different than a lot of instructors. I find PowerPoint slides do one thing really, really well, and that's kind of guarantee that you get a good nap. And believe me, it's difficult to keep people's attention on something when I'm teaching a class live, but when I'm teaching a class over the internet, keeping people's attention is nearly impossible. So I find that PowerPoint slides do one thing well, and guarantee that you get a good nap there. So I don't use them. In fact, this is the last we're going to pop. I may pop in to show you a quick picture or two, but that's the last you're going to see of the PowerPoint slides. I prefer to teach my classes by just demonstrating. So everything that I do is going to be demonstrated in the software here. But in addition to that that directory, let me come back here to my desktop and Inspire Structures. You're going to have this file or this directory here, the exercise. This is where all of the model files are going to be found. For any of the demonstrations that I do, you'll find them in this directory. And for all of the, excuse me, I'm boring myself here. All of the exercises, this is where you're going to find the files to begin each one of them. They're very nicely organized, as you can see here, by the exercise number, or subsequently the chapter number. So exercise 1, 2, 3, 4, 5, 6A, 6B. So you're just going to go to the exercise in that chapter and open up that file. Now, nicely, we have also included this subdirectory, student exercise solved. So you can think of this as the answer key in the back of the book. What you're going to find in here are also Inspire models, but these Inspire models are going to represent what your model would look like at the end of the chapter. So it can provide you kind of a reference to go back and look to make sure that that you did things correctly, or In many cases, the next exercise starts off at where you left the previous exercise, so this kind of provides you the ability to skip an exercise and maybe move on to another one. So you're going to find all of those things in there. So I would absolutely encourage you to go into that chat window and grab that link, download that file, that zip file, and you'll have all of that material. And let me just check here. I don't think we have any questions or anything, but again, please don't hesitate to answer. File types. What is it? Hold on. Oops. Okay. Why is this? Let me pop this thing out here. So we do have a question. See many file types in the exercise folder. What is the difference between XT, XB, STMod? Excellent question. So STMod files. Let me come back to that. Let's come to here and let's move these questions off to the side and exercise. So these STMod files, these are the file type for Inspire. If you want to know the reason STMod, Inspire originally was developed under Altair's Solid Thinking brand, so Solid Thinking model. X_B and I believe X_T, these are two different parasolid files. So I think X_B is binary parasolid and X_T is text parasolid, but those are parasolid files. So those are going to be geometry files. Do you know where? I'll get to that quite in just the next question. I'll get that in just a second. So these two are geometry files, and we'll cover importing those in there as well. The CSV is just an input file for one of the exercises. Okay, the next question. Sorry for having to repeat yourself, but do you know where the link to the download exercise are? I do know where that link is, and what I'm going to do here is I'm going to grab that and I'm going to put it in the text. I think what ends up happening is when you come in after the chat window was sent, oops, or when the chat message was sent, it erases that. So that should be it right there, and send. So that should be the link. There we go. If you just click on that link right there that I just put into the chat window, that should open it up. Let me just double check. Yep, and that's going to take you to this little window right here, and you can just download this zip file. It's a slightly sizable zip file, but it should be able to download pretty quickly. And that should do it for the questions. Again, please don't hesitate to ask any more questions, but let us go ahead with the material here. So I'm going to open up Inspire. I have the latest version of Inspire here, Inspire 2019.2. That is our absolute latest and greatest. I know that if you are doing the student version, to get the student version to work with the special student license, it does take a little bit of time for them to work on that. So I know that our student versions are a little bit behind it, so you may not have access to the absolute latest and greatest. But that would just give you incentive if you are on a competitive team to get that sponsorship, because you can get the absolute latest and greatest with the sponsorship. But that being said, if you're not using 2019.2, there may be a couple of functions that we talk about that you may not have access to, but the absolute core of the class, the setting up the analysis and optimization, aside from the look and feel of it, you're going to find all the functionality is there, so you're not going to be missing out on anything. But this is the Inspire window. Inspire was created a number of years ago as the opportunity for people who previously didn't have the ability to do analysis and optimization. We've kind of opened that ability up to them. So what we can do now is, through a substantially easier to use interface than you would find in any other preprocessor, you're going to be able to set up an optimization analysis. Okay, example files are in 2019, but we are running 2018 and cannot be opened. Download the. Yes, yeah. So what I'll do is I'll find an older version of the files, and I will make those available. I'm not going to be able to do it while we're in the class here. Maybe when I take, you know what, when we take kind of our first break in about half an hour or so, I'll find those and I'll make another download available for anyone who's not running 2019. But 2019 version is available for sponsored teams. Yes. You should be able to get the sponsor. If you have the sponsorship, you'd be able to get the 2019 download. But for those of you who don't have the 2019, I will get you the earlier files, so you'll be able to bring those up and work through the exercises. But you're going to find here, Inspire is incredibly easy to use. So for instance, say I wanted to do a cantilever beam analysis. I just want to toss up a cantilever beam, maybe do a quick check against some hand calcs that I'm working on. If I were to do this in a traditional software, well, first thing I'd have to do is I'd have to come up with the geometry for it. So that would require me going into a CAD system. I'd have to create the geometry. I'd have to bring the geometry into the preprocessor. I'd have to mesh it, make sure my elements are good. I'd have to set materials and properties, then set boundary conditions, and then go through and run it. But literally, and I know literally is used far too often, but in this case, I do mean literally. And literally, the amount of time that it took me to just make that explanation, I could have a cantilever beam analysis running in Inspire here. And I don't even have to go to a CAD system first. I'm just going to come up here to my sketching tool. I'm going to sketch a little bar like that. We'll just leave the values what they are. And now I exit out of there and I just drag that across, and we'll say that we want this to be, I don't know, 3 meters long. And now fit, well, that's a little bit like, nah, whatever. That's fine. We'll leave that. So now I've got my cantilever beam there, and now I'm just going to right click on it, and I'm going to say, what do I want to make this out of? Maybe we'll make it out of medium carbon steel. Sure, that's no problem. And then I want to make sure that it stays in place, so I'm going to come over here and I will get to an explanation of what all these are. I'm going to hold it in place. I'm going to hold it in place right there, and we'll come down here to this end. And I'm going to put, I'm just going to sketch a location on this surface right here. Yeah, that seems about right there. And exit out of that. And then I'm going to come here back to my force, and I'm going to say I want to put a force of 1,000 newtons on that pad right there. And that's it. I'm good to go. I can now come here and I can analyze this. And as quick as that, the analysis is off and running. So you would be hard pressed to even have the geometry loaded into a standard preprocessor, and ours included, and just potentially getting to the point where you want to start meshing it in the time that it took me to entirely set up and have running this cantilever beam analysis. So I'm going to let this process off in the background. This is probably going to take a little bit of time because it is so thin versus how long it is. So it's going to be a sizable amount of elements. But we'll let that run in the background. And while that's going, I'm actually just going to open up another instance of Inspire here. And you can see we're getting along pretty quick. So it should be done in the next couple of minutes. But we'll let that plot along while I open up another instance of Inspire. So that's how I could do it directly with Inspire. But the vast majority of people aren't going to sketch out their geometry with Inspire. What are they going to do? They're going to use a CAD program. They're going to come up with their designs in CAD. Inspire has some great and pretty cool sketching tools. I can, like you just saw, I can sketch a little block there, and then I can take and I can extrude that block out. And if I want to, put a hole in it, I could sketch on this face and drag a hole. And now if I come and I drag it in this direction, I put embossment, or that direction, I put a hole through it. So you can see the tools that we have in Inspire are pretty cool. But the vast majority of people are going to do their design work in CAD, and that's what we've got here. So I'm going to come here, I'm going to select open, and you'll notice we're not even saying import because we want to consider all files as files that can be brought into Inspire. So I'm just going to come here, open. I'm going to come into my student exercise, and I'm going to open up this x_b. And even if you are using Inspire 2018 or prior, you should be able to open up this exercise to x_b because it is just a parasolid file. And this is actually the file that we're going to use through this course. So you really shouldn't even need to access the rest of the STMod files until you want to do some exercises on your own, and I'll have you those files a little bit later on. So you should be able to still work along even if you're using a version previous to 2019. So I'm just going to double click on that. And you see what it's going to do is it's going to bring that geometry in. So this geometry could have been created in, for the students out there, I'm guessing your primary CAD package is going to be SolidWorks. That seems to be the one that is the most popular in education. But even if you're not using SolidWorks, you're using CATIA or UG or ProE or any of the other popular CAD packages in there, you're going to find that in Inspire, we support all of them. All of the different CAD packages that are available, you're going to find in here, and we can just open those natively, or you can use like Parasolid Step as an intermediate format. But we can just bring that directly into Inspire. Now you see I'm kind of rotating this part around. I am doing that by pressing the middle mouse button on my mouse, in my case the clickable scroll wheel, and that allows me to rotate the part. If I want to move the part around, I just hold the left and the right mouse button down together. And if I want to zoom the part in and out, I just use my scroll wheel to either push it in or pull it out, and it will use the pointer as a focus. All of this information you will find in, I told you I'd come back to this just for pictures. You're going to find that somewhere in this PDF here. Display controls. I'm not going to waste too much more time with this, but one of the slides in here is going to outline those mouse functions. And I have for years joked that that software companies that produce GUI-based softwares get together. They all get together in a super secret conference every year at some hidden, unknown location. And they all get together with the sole purpose of making sure that whatever mouse controls they use in their software is completely different from the mouse controls that the other companies are using in their software. To make it so that when you move from one GUI software to another, it's almost like learning a different language, because you're clicking one button, it's making the part disappear off the screen because that was the rotate button. Let's just say Altair stopped going to that conference. If you come up here to the File pull down and you go to Preferences and you come here to Mouse Controls, now this is going to look a little bit different in 2019. In the previous versions, you just have a little pull down here, and you'd be able to select all of the, or any of the different CAD packages out there, and that would redefine your mouse controls. So you see, if I select SolidWorks, it will say default setting for SolidWorks. And in the case of 2018 or previous, it's just going to say SolidWorks there. And what that's going to do is now the mouse controls for panning, zooming, rotating, selecting, whatever, are going to be the same as they are in SolidWorks. So now you can pop from your SolidWorks directly into Inspire and not feel like you're suddenly working with your wrong hand. I'm just going to go back here to default. Now these are editable. If I have my own little way that I want to go about doing it, I can change these, and I can even change them in the formats there. But I'm just gonna leave it on default. Okay, so I've got my model here. Now, one of the more challenging things that that people face when they do analysis setup and optimization, anytime you're using a finite element analysis code, is the establishment of units. And that's because finite element analysis by nature is unitless. It's just math, and math doesn't require units. We require units, of course, to make sure that we understand the numbers that we're putting in and understand the numbers that we're getting out, making sure that they make sense. But the math engine behind finite element analysis does not require units. So units are, or FE systems are unitless, but we work in a world of units. So Inspire uses a set of units, and you can select from here. So we call these unit schemes or unit systems. And those are typically defined by the establishment of three things: a unit of distance, a unit of measurement, and a unit of, a unit of distance, a unit of force, and a unit of time. And they're typically referred to by those schemes. So for instance, MPa, which is the megapascal, is millimeter Newton second is what people typically refer to it as, or IPS, inch pound second. So with Inspire, you can pick any of these unit schemes and it will automatically update your entire model to the new unit scheme. So I can be halfway through setting up my analysis, suddenly decide, you know what, I don't want to be an MPa, I want to be an IPS. I switch to it, and no matter what I've done in my model, everything is automatically updated. So units are truly seamless within Inspire. You will not run into any difficulty with units. And in fact, when I run this thing and I start post-processing it, I can even change units then, and it will automatically update my results to the new units. So I'm going to move into the MPa system. I like the millimeter Newton second system. And from here, what I want to do is I want to run an analysis on this. This little guy right here, let me bring this back up. This is a bracket. There's the picture I want. This is a bracket that holds a door hinge for an aircraft door. As you can see, two of these brackets mount on the frame of the aircraft, two of the brackets mount on the door, and this wacky looking hinge goes in between them, and this is the hinge that allows the door to kind of open outside and tilt and come back, or open inside because they are plug doors, and then tilt and then go outside to let people off the plane. But what we want to do is we want to optimize this this design. This is our initial concept design. Looks nice. Sure, it works okay. But I think we can do better. But to make sure that we're actually doing better, one of the first things that we absolutely want to do is we want to benchmark this. We want to know where we are now. So I'm going to run an analysis on this. To run an analysis on this, I've got the geometry. So the next thing that I'm going to want to do is determine the material for this. Now, there's a couple of different ways I can do this. And the first way, the way I like, of course, as you saw, is just to right click on it and select material from there. But I also want to bring to your attention these windows over here. Now, you may not see them. Your view may look like that. That is the default view for Inspire. The model browser and the property editor, I personally feel, are critical windows to have open. There are other people who don't like them open. They much prefer having this big, wide open design space, and pretty much everything you do within those windows you can do through right clicks and other functions within Inspire. I just like to have them open, and I can open them by either coming to View, Model Browser, and Property Editor, click those on, or you'll see here F2 and F3. So I click F2 and I click F3. Oops, I just clicked F4. There we go. F3, I get my Model Browser and Property Editor. And I like these because you'll see it's going to list all of the parts in my model, and in this case I only have one of them. But if I click that part, it's going to show me the name. I can edit it. We can call it hinge bracket. It's going to show me what materials. It's going to show me what material it's made out of, whether it's part of the design space or grounded, whether the mass properties are auto-calculated or I type in override it. I can change the color of it. So all the information's right there. And then up here in the model browser, it's actually showing me the mass of the part. So that's going to be dictated by the units that I'm in. So it's showing it in tons because I'm in the MPa. But if I were to come here, you'll see if I change this to inch pound second, that automatically updates to 9.404 pounds. And all of the dimensions on my part changed as well. So the size of the part did not change, just the value of the measurement changed. And you'll see if I right click on this and I select aluminum 7075 T6, which is very popular aerospace aluminum, I'll pick that. Look at that, I've already done lightweighting on my part. I brought it down from 9 pounds to 3 1/3 pounds. So now I've established the material. I've got the physical description of the part with the geometry. I have the material description of the part. What I need to do now is start defining the analysis that I'm going to perform on this. And to do that, we're going to come up here and you'll see along the top of the Inspire window, we have these little ribbon tools here. So we have followed kind of the general path of the way that Windows softwares are going these days to move into the kind of this ribbon structure, where you have a large number of functions and they're going to be spread out by type. So if I select geometry in the ribbon, I have all of my geometry tools, and we'll come back to some of these later. In the structure, I have all the tools for defining the structure of my part. And you'll just see here, I have this loads icon. Now, another thing that Inspire does very well and better than pretty much anyone else is the definition of our icon. So a standard icon in most softwares is not much bigger than, say, that little icon right there. The one that allows me to turn on or off the visualization. And for the most part, icons, if you take a look at them, you're hard pressed to figure out what that picture is even of, let alone what that function actually does. Well, we didn't want to do that. We wanted to make sure that our icons were very large, very colorful, very descriptive, showing you exactly what the functionality does. But the only way that we could do that and not have a bazillion big icons is to take similar functionality and group them together into one icon, thus the creation of the multi-function icon. So now, no longer is it just click an icon for a function. The icon itself describes what the functions are, and where you pick on that icon determines what function you're going to do. So these are all of our loads. Our supports are our constraints, our point loads, our area pressures, our moments, torques. So where you pick on here determines what you're going to get. So I'm going to come down here to my supports. I'll click on that. And this is how I can define supports for my model. If you're familiar with finite element analysis, you'd know them as constraints. So a support allows me to hold the part in place. And if I click on any geometry, either a surface, a line, a point, or a cylinder, it's going to put a constraint on there. It's going to put that one symbol on there. But you see, because this entire surface is highlighted in red, what that's telling me is that entire surface is subjected to this constraint scheme. And the standard constraint scheme, excuse me, is fully held in place. So if I want to edit that, all I need to do is double click on that constraint and it will bring up these little arrows. And if I click on any of those arrows, my constraint logo is going to change, or icon is going to change, showing that change. It's showing me these roller balls in that direction, which tells me that this model can now roll or move, slide in this direction. If I click on it again, and now free it up in the perpendicular direction, I get this little caster ball on there, and that's telling me that this entire surface now can move in plane, but cannot move out of plane. Oops. Let me do that again. There we go. So now we're going in the Y direction here, but if you need to change that, so say I want it in that direction or similar to that direction, but I want it, say, 30 degrees off of that, off of the Y-axis. All I need to do is double click on it, click this icon right here, move support. I get these little graphic manipulators, and I can take and twist that to 30 degrees off, and now it's free to move in the 30-degree off. If I choose to constrain a hole, which is what I'm going to do down here, representing these bolt locations, I get a new type of constraint icon, and that takes advantage of the unique geometry of a hole, which is when we put a hole in the part and we constrain it, we're typically doing so with either a bolt or a pin, and that means there never can be motion perpendicular to the axis of the hole. But by double clicking on it, I can allow or free up motion that rotates around the axis and or motion along the axis, but it will always remain constrained perpendicular to the axis. And now I can go through and select the rest of these. And what I'm doing now is I'm holding my part in place. I'm mimicking the constraining or support schema of bolting this in place. So now it's held in place. Next thing I need to do is apply a force. So I need to tell it what sort of forces it's going to be seeing. And again, I can click that. It's going to apply, in this case, a 1 pound force across that entire surface. And just like with the constraint, I can change the direction, make it plus or minus, and I can even rotate it if I want as well. But I want to apply this to the hole, so I'm going to select that. It puts it right at the center of the hole, but you'll see the surface of that hole highlights or turns red, so that tells me that it's applying it to the entire thing. And I'm going to put it, we'll say in, oops, what do I want? The X direction. I could type in here, say 400, and that would be 400 pounds force. But say, for instance, when somebody reported to me the force that they wanted this analyzed with, they gave it to me in newtons. Well, I could whip out my calculator and do the conversion, but I don't need to bother. I can just come in here and say, okay, 2,000 newtons, and you see it automatically converts it to pound force. So if I just type in 2,000, it would be 2,000 pounds of force. But if I put in the abbreviation for the unit, it automatically converts that for me. Now that's one load case when the door is closed and it's pulling on the hinge, but I have another load case, in this case where the door is open and it's pulling down on the hinge. And again, I could say, this one may be 1,500 newtons. And so now I have two forces acting on there. The problem in this case, though, is those two forces are going to act at the exact same time. So it's going to do a little vector math, come up with an equivalent load, and that's not what I want. The door can't be open and closed at the same time. I can never have a situation where these two forces act at the same time. But yet I want to analyze the part, take into account both of these. To separate them, all I need to do now is come up here to my force icon or load icon and click this little, what looks like a little piece of paper here, and we have our load cases. You'll see as I highlight over these, each one of my forces and supports is shown here. And if I want to, I can add another load case. And we'll see here, so this is my door open, that's my door closed. So let's change this, let's rename this to door open. And we'll right click on this and rename this to door closed. And from here, this looks okay, that's my door closed force, so I'm going to turn that off here and turn that on here, and then I'm going to say I want to use all of my supports, so I can create as many different instances as I want. Each one of them will run in the analysis, but they will run independently, so I will be able to see results for each of these independently. And I could add as many as I want. Other load scenarios that I have, in this case, is enforced displacement. So maybe I don't know the force, but I know that this point moves 7 millimeters in the x direction. I can enforce that displacement. I can put angular velocities and accelerations, g loads, define the direction and the acceleration of gravity, apply temperature loads, apply non-structural masses, so masses that are hanging out that don't have a physical description of them, just the location of the CG and the mass. And I could do any or all of those and create multitude of load cases. In this case, I'm good with what I've got. So I come over here to my little analysis icon. I click the little play button underneath it, and it brings up this window here. Now, we've seen this window once before. If you remember with our cantilever beam, which, by the way, is done. So let's take a look at the results of that. And I can view the animation on this. Oops, I hit help accidentally. And we can see that this thing, for as thin as it is and as long as it is in pretty bad shape. I've got a 1 factor of safety. I'm well over my yield stress. And you can see I've got a ton of stress on this. If I change this to actually represent the properties of my aluminum, or in this case steel, you can see everything from here back is beyond yield. So I've perhaps overdone it a lot with my little cantilever beam. Okay, so coming back here, we kind of breezed through the analysis window when we ran our cantilever beam, but in this case, we're going to go through each of it. I can give it a name. I could call it door hinge bracket benchmark. Oops. Now you're not going to have to worry about the meshing in here. Inspire is going to handle that all on its own in the background. And it's going to do so quite well. It's actually going to invoke a tool of ours called SimLab, which does a fantastic job of generating a mesh behind the scenes. So you don't have to do anything with the mesh, but we also don't want to limit you from being able to alter it. So it's going to automatically calculate an appropriate mesh size, but you can override that by putting a new number in here. I can tell it I want to do a normal modes analysis and indicate how many normal modes I want. I can do buckling mode analysis and how many buckling modes I want. I can do speed versus accuracy. This is going to be meshed with tetrahedral elements. What ultimately happens is with the faster, it's going to use first order tets, and with the more accurate, it's going to use second order tets. Unless you are in such an amazing rush that you just can't possibly wait for the more accurate, and even then I would encourage you to wait for it, stick with the more accurate for the analysis. The results that you get from second order tetrahedral elements are phenomenally accurate, whereas the first order tend to be a little bit stiffer and your stresses tend to be a little bit higher. We'll talk about contacts later. Do I want to incorporate gravity or not? By default, it's off because we don't need to complicate things if we don't need it. And in this case, this part is not going to be affected by gravity. It's too small and stocky that it's not going to have any overhangs that are as a result of gravity alone. But had I decided to put it, maybe I didn't want to simulate it by putting these forces in here. Maybe I wanted to simulate it by putting the mass of the door at the CG of the door. Then, of course, I'm going to turn on gravity. And then finally, which load cases do I want to analyze? By default, they're all on. I'm going to leave it that way. I'm going to click Run. So while this takes a couple minutes to run, I just first of all want to say, are there any questions? Okay, then in that case, no questions. What I'm going to do is I'm going to pause things here. I'm going to grab the older version of the Inspire material, and I'll make that available for anyone who wants to download it so that they can utilize it on whatever version they're doing. So I'm just going to come here. I'm going to pause the recording. Okay, so let me restart the recording here. Okay, we are good. And it looks like it has updated now and the analysis is done. We will open up the results of the analysis shortly. I do have that question that I want to get to before I move on. But again, in the chat window, the last chat that I just sent is a link to the material, the 2018 version of the material. The class is essentially exactly the same. It's just as the model file should be compatible with 2018. But before we move on, I did get this rather intriguing question here. What is the difference between Hypermesh and Inspire? Which is better to use? Well, that's a really good question that would to answer in its entirety would take quite a bit of time. But the short Cliff's Notes version of the answer is the main difference is Inspire is substantially easier to use. But to accomplish that, there are some limitations to it. Inspire is actually using HyperMesh in the background to set up the analysis. So the capabilities, there's nothing you can do in Inspire that you can't do analysis-wise in HyperMesh, because it is utilizing HyperMesh in the background. But Inspire, you can do things a lot easier, a lot quicker, and in almost every case, immune to mistakes that prevent an analysis from running. But to accomplish that, there is a reduction in the capabilities. So for instance, I have very little control over the mesh in Inspire. I can give it some general mesh size, but it's going to mesh the entire part that way. If I need to do mesh fine tuning, I need to partition off areas and give those areas a smaller mesh size that overrides the global. So I don't have as much hands-on ability to affect the analysis. But that being said, Inspire kind of follows the whole concept of the 80-20 rule, that 80% of users are only going to use 20% of the capabilities of a software. And so what we're focusing on is taking Inspire and really making sure it can do those 20%, and in fact with Inspire nowadays, probably well more than 20%, but make sure we can handle that subset very well within Inspire and very easy to use. And then if you need to move beyond that, you would have to use HyperMesh. I would say the biggest thing, the most common reason for moving to HyperMesh from Inspire is strictly limited to isotropic materials. Isotropic homogeneous materials, which means if you need to do something that's orthotropic, like for instance a composite material, you would have to go to HyperMesh to do that. Now that being said, Inspire is going to incorporate composites eventually, but they're just trying to find out, try to work out a way to do that along with the other million things they want to do, but make sure that it's still easy to use. So I think the short answer would be they're both excellent softwares. HyperMesh can do everything. Inspire can do a subset of HyperMesh, but can do it substantially easier. Another question, I'm new to both HyperMesh and Inspire. Do either softwares calculate unknown forces acting on a part? I assume you're talking about, say, like reaction forces or something along those lines. So actually, HyperMesh and Inspire are preprocessors, so they're not going to calculate anything. It's going to be the solver that's going to calculate things like reaction forces. Both of them use OptiStruct as the solver. But only in HyperMesh can you set the parameters to request reaction forces from the solver and then be able to obtain those. So HyperMesh allows you to request that information from the solver. Inspire does not. It may someday, but right now, no. Okay, but we have now got our results. So I'm going to come here. I'm going to click on the little green flag. Great questions, by the way. I appreciate the questions. At least lets me know that I'm teaching to someone out there. A lot of times, a lot of these webinars, I get nothing, and it's like, is anybody out there? So keep up the good questions. I appreciate it. Okay, so I've got my result here. I want to come here to my von Mises stress. I can see a little bit going on right there. If I click the animate button, I'm going to be able to see how this part is moving. We do automatically scale up the animation. This is in absolutely no way an actual representation of the deformation of the part. If that were the case, get off that airplane immediately. That's bending way too much. We automatically deform it, or we auto deform it because we want you to be able to see the behavior of the part. typically, by definition, if you're running a linear static analysis, if you can see the deformation, you're probably deforming a little bit too much. But what I can do is I can come here to this icon. I can see that, oops, hold on, I gotta move these controls here so I can see what's going on here. Okay, so I can come to, there it is. I can see that it's auto scaling 502 times. If I turn that off and click 1, so there's the actual deformation, and you can see that I really have to zoom in quite far to even begin to see that deformation, which is why we automatically scale it up. So don't be surprised when your part looks like it's made out of rubber. That's just the auto scaling. And it looks like we've got another question here. What did we get here? Can I have a look at the mean stresses, for example? So you're going to have a lot. Can we use Inspire? Oh, there was one here first. Can we use Inspire for CFD analysis? No. We've got other tools for CFD analysis. AccuSolve is going to be our solver for CFD. If you're looking to do wind tunnel studies, we have a tool called Virtual Wind Tunnel, which has the look and feel and the ease of use of Inspire. And you can bring in the mesh from a car, for instance, and very easily set it up for a wind tunnel analysis. But no, in Inspire we can't do CFD. And then we've got a question here, can I have a look at the mean stresses, for example, as well? You're going to have a lot more capability of viewing results in HyperView, which is our full-blown and the next question, I'll get to that in a second, which is our full-blown post-processor. You'd use that in conjunction with HyperMesh and OptiStruct. All we have result-wise in Inspire is what you see here. So I'm going to see my my von Mises stress, my max shear stress, and I can see the principles. But I can't get anything more from that. But the next question, which was, can I see the minimum and maximum? Absolutely. In fact, we have this little button down here, min and max. If I click that, it's going to give me a little call out showing me where the minimum and where the maximum stress lies. It is going to provide me this contour using what we call a divergent scheme. The divergent scheme was developed to allow you to focus on the three things that are critical or that we want to understand in a linear analysis, which is what's below yield, what's at yield, what's above yield. I can change this to the standard rainbow plot just by coming to these little lines, clicking legend colors, and then I would just come to von Mises and I would change that to rainbow and click OK. And then now I can see that. Now this is going to be based upon the maximum in stress. If I change this to the values for the material, you see all the stresses essentially go away, because now what it's done is it's assigned red as anything that's above the yield stress of the material. Oh, you're welcome. You can ask for other callouts as well. So maybe I'm interested, and I'm going to stop this animation just because trying to grab things as it's animating. Let me bring this back to, there we go. It's kind of difficult. So maybe I'm really interested in what's going on at this corner here. It doesn't happen to be the max or the min. So I just come here to my call out. I click that right there, and now I get the von Mises stress there. Now that's the door open. If I click door closed, you see that call out stays the same because I specifically asked for it, but my minimum and maximum have now changed because this is a new result now. So this is going to be my door closed. So the minimum and maximum have changed, but my call out has remained. If I click compare results, it will allow me to see the result envelope is when it just takes and combines everything, but it allows me to compare the results, the maximum and kind of the stress distribution for my two different options right here. And we've got displacement, factor of safety, percent of yield, tension and compression, which is von Mises, but signed von Mises, and then the shear and the principles. The yield stress, where it's getting the percent of yield and the factor of safety, if I come to my materials here, I can look at all the materials in my library and it will tell me what the yield stress is. That's where it's getting that value. And I can add my own materials by just coming to my materials, click plus, and then I put in the values that are needed. E, nu, and rho, so the Young's modulus, the Poisson's ratio, the density, then the yield stress, and the coefficient of thermal expansion. Okay, so now we've gotten through our benchmark. We understand where we are right now. But I think we can do better. This part, as we mentioned, weighs about 3 1/3 pounds. And because my stress results are so good, I mean, if I come here to factor of safety, you can see that I can't find a single area that's below a 6 times factor of safety. In my door closed, in my door open, I've got the same situation. So I've got a 6 times factor of safety. That's devastating, especially when it comes to an aircraft part. Not because I want to make parts that aren't safe, but because this part is too safe. It means it's over-designed. And I put this on my aircraft, and I'm going to be flying around pounds of aluminum that are unnecessary. So I know now that even though there has been some light weighting applied to this, putting these little pockets in here, shaving these corners off, it's not enough. And this is kind of the standard way of doing light weighting. You put a pocket in here. You do an analysis where there's no stress, you shave it off. Poke a hole through it. That's worked okay for years. But now it's time to kind of step up our game and take advantage of what we call simulation-driven design, which is using a simulation tool to actually help us design our part. And what that means is I'm going to come here and I'm going to be doing an analysis or an topological optimization on this. Topological optimization is a tool that allows us to determine what material is necessary and what material isn't. You can compare topological optimization to sculpting. If you were to go to a sculptor and ask them, how do you do what you do? They're going to say, much like Michelangelo said, 600 and some odd years ago, that as he put it, when I look at a block of marble, I don't see a block of marble. I see the statue that lies inside that block of marble. And as he said, I have only to hew away the rough walls that imprison the lovely apparition to reveal it to other eyes as mine already see. Which in ancient Italian sculptor to English translation dictionary basically means when that marble cooled millions of years ago, that statue was formed. And it's Michelangelo's job to take and get rid of all the additional marble that is in the way of the statue that's already there, the statue that he sees within that marble. Topological optimization is the same way. If I take and generate a chunk of aluminum and I strap it onto an aircraft and strap a door to it, somewhere inside that block of aluminum is the ideal part. The part that uses the least amount of material but does the job that I'm asking it to do. And that's what topological optimization is. And that's why topological optimization is so powerful, because it analyzes the part. It uses analysis to determine what material is necessary. It's not like these other companies that are coming up with these kind of bogus, weird ways of generative geometry design, which is just kind of taking some theories and ideas and a lot of user-driven information to just kind of generate these geometries. This isn't just coming up with bogus geometries. This is actually developing a geometry based upon an analysis. So it's not generative design. It's actual analysis-driven topological optimization. And so what we need to do that is we need to take this part and we need to create a nice big block of material out of it. So just like a sculptor is not going to take a sculpture that already exists and carve a new one from it. They want to start with a brand new, fresh block of material. That's what I want to do here. I want to get rid of all of these features that were done to lightweight the part, because maybe the ideal part has material running through where this hole is here. So I'm going to convert this into what we call a design space. Now that could be done in your geometry software, in your CAD package, or it could be done in a lot of ways, a lot of cases, far easier here within Inspire. All I need to do is come here to my geometry tool, and if I come to simplify and select holes, what holes allow me to do, if I pick a hole, it makes that hole go away. Of course, I don't want that to happen, so I'm going to undo that. I want to get rid of these pockets, but you see it hasn't identified them. All I need to do is come to the bottom and double click on that bottom. It finds the hole, click again, and it goes away. So I'm getting rid of these little pockets here. And as you can see, I'm also increasing the mass of the part, which is fine. I understand that, because my goal is to get this big block of material and then determine what material is necessary from that. Now the next thing I have are these little shaved off corners here. So I'm going to come to this push-pull, grab that face and drag it out. Drag it out. Drag it out. And now I have a nice big block of material from which I can determine the material necessary using topological optimization. And to do that, all I do is right click on this and say design space. And what design space does is it says, okay, this is the material from which you're going to carve your part out of. But that leaves one slight problem. There are aspects of this part that have to be there. This cylinder right here, if we come back and we look here, that's where this hinge is going to mount to this bracket. If that cylinder is not there and not perfectly round, I cannot mount the hinge to it. And if I'm telling the software, carve away what you feel is necessary, it has absolutely no reason to keep that as a perfect cylinder. So I need to force it to. And to do that, I'm going to come here to this tool that we call partition. Partition allows me to select that hole, tell it how thick I want it to be, say 0.2, And now what it's done is it's broken that out into its own separate solid. You see it's not the red of the design space. And so when it goes through, when the topological optimization goes through and gets rid of the material to lightweight it, it will leave that cylinder alone. Now you'll notice one slight quirk here. In doing that, I also lost my loads. So I'd need to recreate those. And then I'd go through and I would do it to these holes down here. So I'd come to partition. But you'll see if I click that, it's actually going to save this entire little box here, which is absolutely not what I want. All I want is a little cylinder. Well, the reason is it's connected to this box here. So I'm just going to hold the control, grab that face down there, and then I click the cylinder, and it will create my little cylinder there. And I could go around to do the rest of the parts, but I'm not gonna bother with that. What I'm going to do is I'm just going to come here because then I would have to go through, create my constraints and my forces again. So I'm just going to cheat and come here. I think exercise 5 is what I want. Yep. Nope. That's absolutely not what I want. Maybe 6A. There we go. Okay, so now we've got our big block of part. I can right click on this, select that as the design space. And I've got my little partition areas here and my bolts. And I'm ready to run an optimization on this. To do that, I'm going to come to my structure tab. And I'm going to come over here to my optimize. I'm going to click that little play button on optimize, and it's going to open up my optimization window. And what we have to talk about now are the different types of optimization that we want to do. And the type of optimization that we pick, and oftentimes we pick multiple types of optimization, run different ones, and then establish a part from that. But the optimization that we pick depends on what our ultimate goal is. And that's what we have to do when we talk about an optimization, is we have to have an objective. What is our final goal? Well, the first objective we have is maximize stiffness. So maximize stiffness, the goal of this is to make the part as stiff as possible, which is ideal, of course, in a situation where we're holding an aircraft door on. Stiff as possible is good. So if I were to set that as my objective, and I'd say, okay, take this part and make it as stiff as possible. I don't think it takes much to realize what the answer to that is. And the answer to that is, okay, don't do anything to it. There you go, part's as stiff as possible. That really didn't help me much. So the other main thing that we need for an optimization is not only the objective, but what limitations are we going to apply to this to obtain that objective? And in this case, the limitation that I'm going to apply is what we call a mass target. The default being 30%. So my target is to only maintain 30% of the mass of this part, but make that 30% as stiff as possible. So you kind of see what's happening here. We're crafting a solution. We're crafting a way to optimize the part. Our goal is to get a stiff part, but we want to get rid of 70% of the material to do that. Well, what that's going to do is it's going to force the topological optimization algorithm to very, very specifically and carefully pick which 30% of the material that you want to remain. And that's where the differentiator between topological optimization and generative design is we're picking the best material to remain and getting rid of all the rest of it. It looks like we got a question popped up here. Is there an option to optimize with a certain machine? Oh yeah, we will absolutely get to that. Give me just a couple of minutes and we will get to that. So the question being, can we incorporate machining methods in this, manufacturing methods? Yes, we can. So this is get the part as stiff as possible, but get rid of 70% of the material. And then do I want to incorporate any frequency constraints? So do I want frequency to come into play here? Do I want to make sure that I maximize the frequencies or make sure I don't go below a certain minimum frequency? And then finally, how thin can any member of my part, any resulting piece of my part get? The other option that we can choose is minimize mass. So if my goal is to minimize the mass and I say nothing other than that, and I say to the solver, okay, hey, solver, minimize the mass of this part. Well, what do you think it's going to do? There. That's the minimized mass of the part. Get rid of all of the design space. Well, obviously that's not an acceptable solution. So we have to, again, give it some sort of limit. How far can you go? So the previous one was, I'm not going to get rid of anything, so I'm going to force you to get rid of something. In this case, it wants to get rid of everything, so I'm going to force it to keep something, and I'm going to do that by setting a stress limit. So how much stress am I going to allow on my part? And I'm going to define that through the use of what we call a safety factor. So going back to our material definition, you'll remember we had the yield stress value in our material definition. And now with the safety factor, what I'm going to do is I'm going to take that yield stress, because that's when my part officially fails, and I'm going to divide it in this case by 1.2. And whatever that value becomes, I'm going to set that as a limit to the stress on my part. So as the optimization code begins to remove material to minimize that mass, stress is going to increase in the part. Less material to handle the force means higher stress in the part. So now, just like before, it has to very, very carefully and intelligently select the best material to remain to make the part as light as possible, but adhere to this safety restriction. And again, frequency constraints. So that's the basics of topological optimization. We also have, a tool or an option where we can maximize the frequency, but since frequencies can also be incorporated into these other two, that would be if we just want to maximize the frequency. Now there's one other thing that we haven't talked about that was actually brought up in the question that came in, is what if I am limited to manufacturing this in some specific way? Well, if I just arbitrarily maintain material that is necessary for my design, that material potentially could be placed in a manner that can't be manufactured. And the best, most incredibly optimized, lightest weight, strongest, cheapest part that has ever been designed is completely useless if you can't manufacture it. Now times, they are a-changing, and the advent of the age of additive manufacturing in a lot of cases is eliminating the need to care about manufacturing constraints at all, because you can pretty much 3D print just about anything. But while 3D printing, or additive, if you want to get technical, if additive manufacturing has the ability to create just about everything or anything, any design you could possibly wish, it has two huge problems. First of all, in many cases, it's prohibitively expensive. And in a large majority of cases, the productivity just isn't there. If you take a look at the main industries that are focusing on additive manufacturing right now, it's the aerospace industry. They are going absolutely nuts with additive. And why? How many rocket ships does SpaceX make in a year? 2, 3? How many airplanes does Boeing make in a year? How many jet engines does GE make in a year? We're talking in the hundreds, or at most in the thousands. How many automobiles do you think Chrysler, GM, Ford, Honda made in the year? Millions. And there's just no way that additive can be scaled up to that yet. It'll happen, but it's not there yet. So additive may ultimately be and probably will ultimately be the solution to everything. But right now, we're not there yet. It's expensive, and it has limited production capabilities. So if we want to maintain certain manufacturing requirements, we need to come back here, and before we run the analysis, we need to establish shape controls. And that's what these guys are right here. The first of which that we're going to talk about is not necessarily for manufacturing, but is symmetric shape control. I have asymmetrical loads here. This force is pointing in this direction, which means across this plane of symmetry, my part is going to be non-symmetric. But if we look at my design here, this same part mounts here, but then gets flipped over and mounted here, which means that anything the optimization tool does to account for that load in that direction is going to be in the exact opposite direction when I take a part and flip it to the other side. So what I'm going to do in this case is I'm going to come here, select my part. It's going to establish 3 planes of symmetry. I'm going to turn off the 2 I don't care about and leave that plane. Now what's going to happen is anything that it does to account for either of these forces, it's going to be forced to do it on both sides of this plane of symmetry. Manufacturing constraints, we have single draw, split draw, extrusion, and overhang. Now you notice these are manufacturing constraints, and the question that was asked was specified machining. Well, we don't exactly have machining constraints, but what we're going to do is we're going to talk about what these manufacturing constraints truly are and how we can equate them to the concept of machining. So single draw and split draw. What those do is they guarantee that we have a part that is manufacturable. So if we come and we take a look at traditional manufacturing methods, stamping or casting. So if we talk about stamping, you've got a sheet of metal there, and you have a punch here, really poorly drawn punch, but I'm doing this with my mouse, and you have a die here, And that punch comes down and it pushes this into this shape in here, and then the punch retracts, and we need to be able to get the part out of there. Which means we have a limitation to how our part can be designed. We are limited to 90 degrees. We cannot go over 90 degrees. If I go over 90 degrees, first of all, I'm not going to be able to get my punch in there, and even if I couldn't get the part out. And actually 90 degrees usually isn't used. We always build in some sort of draft angle here. Same thing with casting. So what's casting? Casting is I take a shape, I fill it with some sort of molten material, and I allow it to cool. And then I take and I flip this thing over, and I need that to pop right out. Well, what if my die looked like that, and I filled that with molten material? There's absolutely no way that that could come out. Or if instead, it came in like that, or it had a hole running through it, there's no way that that could come out of there. So what the manufacturing does is single draw is just one direction. Split draw is kind of like our die, but instead of just one, you actually have two dies come together, and it allows you a little more freedom in the shape, and then those dies split apart. Extrusion, the extrusion manufacturing process is to take some sort of semi-molten material and push it through a shape, and then we get a constant cross-section coming out the other side. What that guarantees is we have a continual cross-section running through the part. How that affects, and actually, let me show you here. I've got this in here somewhere. This is the only other slide I typically like to show. I should probably memorize these page numbers, but I won't. I always say I should, and I never do. Okay, so there's my symmetry. Draw direction. They went and changed the slide, I think. Oh, that's a bummer. There's a really good slide showing the difference in shape controls, but yeah, this will work. So in the case of this block right here, single draw is going to guarantee that it would be cast or stamped in one direction. Split draw, you see, allow kind of this undercut here, but you could see how you could take two dies and split them apart. And then extrusion guarantees that you just have a constant cross section running through. How can I relate these two in the manufacturing process? Well, you can think of single draw as machining coming in from one direction. So if I were using a CNC tool and coming in from one direction, split draw is if I'm coming in from both directions, and then extrusion is as if I'm laying this and doing either laser or water jet cutting on it. So that's how we can incorporate manufacturing and machining constraints in there. Final option here, overhang. This was a new one that was added to accommodate additive manufacturing. I said that you can create just about everything with additive manufacturing. That is true, but anything that hangs out too far, you also then need to 3D print some sort of support structure in it. And what this does is it allows you to provide a manufacturing constraint that does not require you to have a support structure by limiting what the overhang is. Now I can run this and optimize it. This will take about 4 or 5 minutes to run. So what I'm going to do is I'm just going to come here and I'm going to open up the result, which is that right there. So this is what the optimization tool has determined is the optimized shape of the part. Very organic looking, it's very cool looking, and it is better than the generative design because this one was actually developed using simulation. From here, all I'd need to do is click Analyze, and it will run an analysis on this exact part, and I can see the deformation and stress results from there. If I want to get this back into my CAD system, you got a couple of options. In the version 2019, we actually have this little button here. It says Fit Poly Nurbs. If I click that, excuse me, what it's going to do is it's going to fill that in with geometry. So now this is solid geometry. And I could take this and I could send it to my CAD system. Prior to 2019, give it a second while it finalizes this geometry. We still have the capacity to do it, but we just have to do it a little more manually using our Poly Nurbs tool. So with the Poly Nurbs tool, let me turn off that geometry there. If I come to Poly Nurbs, I come to this wrap, and then with the wrap, what I do is I move. You see, it puts my part into kind of a faded, and it detects the cross section. I can drag these little tubes here to define cross sections, and then as I create them, what I can do then is stitch them together using this bridge tool. So I click this face and that face, and it will bridge those faces together, and I can create the part that way. It takes a bit more effort. It's a bit of a smoother design that it comes up with, but it's something that really really takes a bit of time learning how to do. So that took us right to about 5:15 Eastern time, which is exactly where I wanted to be when we were done here. Because now I want to give the remaining 10-15 minutes of the class, open it up to questions, and then just recap some of the things that we've done. So we'll spend about 5-10 minutes if anybody has any questions. Oh, I see one came in already. Does Inspire have the ability to optimize weldment parts such as car or bike frame, tube diameter, wall thickness is necessary at certain locations? Not exactly. So if you design your tube using surfaces, what you can do is you can run a gauge optimization. And what that's going to do is it's going to calculate the ideal thickness of the surface. So you're representing a tube with just so you're representing a tube just with a single zero thickness surface that you apply some thickness to, and what it will do is it will optimize the proposed thickness of that. But for weldments, we don't have the capacity to optimize things like that. Another question came in. Where's the questions? There it is. Can we obtain a smoother design in the 2019 version? Yeah, so you have the automatic generating Poly Nurbs tool or the manual Poly Nurbs. The manual Poly Nurbs are going to give you a smoother result. If you want to see here, I don't know whether it's in this. I hope it is. See, nope, desktop. Our structure is solved. Optional final, no, that's, oh, I'm going to be sad if it's not in there. No, that's not it. Darn it. I had hoped it used to be in there. Let's 13 final. Let me grab some of these. No, that's not, definitely not it. I think that's the motion. I don't know. There's a, there was one model. It used to come with the class that would show you what somebody had done to that door hinge bracket after they finished with Poly Nurbs. And it used to actually be named bracket final or something like that, but I don't know if it's still in there. If it's not named something convenient, which is of course most unfortunate. Oh, definitely not this one because it's not 13 pounds. Darn it. Oh well. Yeah, somewhere there's a model. If you come back on, if you're coming to the motion on Thursday, I'll track down the model somewhere and I'll just do a quick show of it so you can see it. But that would be, oh, nope, darn it, that's not it. Unless, nope, that's not it. Then that's maybe 12. Fingers crossed. It's not 12. I'll track it down and I'll show it to you on Thursday if you come back. If you don't come back, sorry, I can't help you out. But no, that's the lattice, maybe. And yeah, I don't think it's in there. Sorry, but yeah, like I said, if you come back on Thursday, I'll show it to you. And looked like there was another one. Questions. When I have optimized part, can I export the mesh to hypermesh? Actually, you don't even have to. It's actually kind of cool if you come here and you go into your documents directory, Altair, the version of the software you're using, Inspire, and Optimization. And if we look here, so what is today? 9.3. Where is 9.3? Or wait a second. 2019.2. There we go. Optimization. So this is the optimization that no, it's not. Oh, because I didn't run it today. Darn it. Okay. I just opened up the results. But if you go into optimization, the results from your optimization are here. You can actually open up the FEM file or the result file. So these are all of the results from OptiStruct, and you could open them up directly in HyperMesh. If you want a mesh of the deformed shape, you can do that by exporting a shape from Inspire. I mean from HyperView. What do I use to optimize the transmission mounted brackets? You can use, absolutely use Inspire. What you could do is model them up, lock them in place like they were held onto the frame, and you could just take and put a mass, point mass with the mass of the transmission at the CG of the transmission and just connect it to the parts and optimize it that way. Oops, lost. There we are. Why did the optimized parts go to each bolt? What if force required? Excellent question. So let me come back to that that result there. So you will notice here that it did not come to these two bolts right here. And the reason it did not come to those two bolts is because you notice here, the topology that was run was a minimized mass with a safety factor of 1.5. Well, let's think about what minimized mass does. Minimized mass gets rid of any bit of material that is not seeing stress above the safety factor. So what this is telling me is that these bolts right here, there was no stress or little stress occurring in these members right here, so it found them entirely unnecessary. But I guarantee you, had we run this not as min mass, but instead as maximized stiffness, where the goal is to make the part as stiff as possible, then it would absolutely have grabbed onto those bolts because it's going to find any way that it can to stiffen the parts, which means grab onto everything that it can. Now, if you wanted to run the min mass and you wanted to make sure that these stuck around, you could put a bogus force onto there that would cause stress to occur in these, and then it would force a connection between them. But effectively, it's seeing no stress in here, so it's determining that they're not necessary. The other thing is, unlike the generative design people who are going to tell you, you know what, our software is going to design the part for you. Don't listen to that. If that were the case, if there were software to design parts for you, then you're wasting your money seeking an engineering degree. You should just learn how to run the software. Our software is a tool to provide you information to help you design the part better. So what you would do in this case is just say, you know what, I want to latch onto these, so I'm going to design another leg to go there. Can I change the working directory? Yes, you can. Come here to File, Preferences, Run Options, and where it says Run History Path right there, whatever you set that as, that's where all of the files that I just showed you are going to be written to. The default is always in your Documents directory under Altair and then the version number Inspire, but you can put that anywhere you want to go, and then it will save that in there as well. Or not as well, instead of putting it into that default one. You are most welcome. So what I want to just do in the last couple of minutes we have here, just let me bring up this, there it is, this slide again. So again, if you are on a competitive team, please contact us for sponsorship. Love to help you out. If you are a university student, not on a team, you can get the student version. And if you see this as a tool that could help you out in school, please get your hands on it. If you want to contact me, if you got a professor or if you are a professor and you think this is something that that could help you out, we do provide software, either honestly either cheap or substantially reduced price to universities. In some cases, we can even get lower than that. to assist you in your curriculum, please get in touch with me. I'm happy to talk to you and help you out there. And if you're a student, if you think this could be used in a class, please get in touch with me or have your professor get in touch with me. Love to help you out. Can Inspire utilize multiple? Yeah. Oh, excellent. Another excellent question. Multiple cores. Yes, and really good question. So if I come here again to my run options, preferences, run options, you will see here number of CPU cores, and you can pick your number of cores from there. I've got it limited to 2, so it doesn't bog down my system, but if I were running this stuff for real, I'd bring that up to, well, I've got, what do I have, 8 core, 4 cores hyper-threaded, so. No. So that brings us to the end here. I appreciate your time. Excellent questions. Really appreciate those questions. Makes my job that much more enjoyable knowing that that I'm talking to people who are actually listening and getting something out of this. So I appreciate your time. Got another question that came in here. Will this be emailed to us? If you can keep a secret, we are recording this. We typically don't make a point of letting people know in advance that we're going to be recording it, because then that just kind of encourages them to not show up and just hope for the recording. But between you, me, and well, everyone else who listens to this recording, yes, we are absolutely recording it. You will be provided a link to that recording. Usually that happens towards the end of the series, but in the past they've been known to send it out earlier. You will get a link to this recording where you can view that. And if you invite me to your school, help me get it into the curriculum, I always come equipped with flash drives with all of the recordings on them as well. So please don't hesitate to get in touch with me. I'd love to help you out. Appreciate your time. Hopefully you got something out of it. We will be back same bat time, same bat channel on Thursday, 3:30 Eastern time, starting about 3:35 Eastern time, where we are going to continue the discussion of the really cool things that we can do with this little motion tab in Inspire and allow us to simulate dynamic systems and utilize that motion analysis to drive structural and optimization analyses as well. Have a fantastic evening or rest of the day, and we'll talk to you all again on Friday. Or I'm sorry, no, not Friday. Don't be here Friday. I won't be here Friday. On Thursday. Have a great evening, and thanks again for your time.